Kinematic equations in two dimensions really come down to two things. Breaking vectors into their components and then applying those components to the kinematic equations that we looked at in chapter 2. We've already been using some of the notation that we would use for kinematic equations in two dimensions, but let's look at it more thoroughly in this video. So we see in this first picture here, we have this guy kicking a soccer ball, and it has some displacement along here. S is the total displacement. But this is a vector, so S is described both by its magnitude, the length of the vector here, as well as this angle, theta. And because it's a vector, we can break it up into components, right? So there is some displacement in the x direction. We'll call this is really a delta x for our x displacement, and then we have some y displacement as well, so we can call this a delta y. And then going back to what we did with vectors previously, the total displacement would just be solving this triangle here, and we can say that our total displacement, the magnitude of this displacement, would be equal to just solving Pythagorean theorem here, delta x squared plus delta y squared. And we could also find this angle theta would be, if we knew the x and y components of the displacement here, theta would be the arctan of the y displacement over the x displacement, just solving this triangle here. If we were given it differently, let's say we were, instead of being given the delta y and delta x, let's say we were given the magnitude and the angle, then we could have we could find the y displacement. We can say that delta y would be equal to the magnitude of the displacement. This is just solving the triangle here, so s times the sine of the angle theta. This comes from solving the triangle, and we could have said that delta x would have been s times the cosine of the angle theta. And so in two dimensions, all we're doing is we're really just looking at vectors applied to the kinematic equations. So we can break displacement into delta y and delta x, like we've actually seen in previous videos. And we can do this with every vector. So not only was displacement a vector, but velocity was also a vector. So we could be given here a velocity prescribed with some magnitude at some angle theta, and very similar to how we solved the triangle for the displacement over here, we can say that the velocity in the y direction is equal to the magnitude of the velocity times the sine of the angle theta, and the x component of the velocity would have been the magnitude of velocity times the cosine of the angle theta. And so velocity can be broken into x and y components, displacement broken into x and y components. We can also do this with acceleration. Let's say that we had some acceleration prescribed the same way. So here's our acceleration vector given in standard position, some angle theta. We can say that our x component of the acceleration would be equal to the magnitude of the acceleration times the cosine of theta, and the y component of the acceleration would be the magnitude of the acceleration times the sine of the angle theta. So we can start to apply this to real life type problems. Let's say, for instance, we were in a boat and trying to cross a river here. So we have our boat facing this way in the positive y direction, based on our coordinate system over here. But the river is moving off with some current in the positive x direction. So let's say we just want to know how we're moving there. We could find the total velocity, given that we had the velocity in the boat. This would be velocity in the y direction would be equal to the velocity of the boat as given in this figure, and velocity in the x direction would be the velocity of the river. And then we can just say that our total magnitude of velocity, which would be the speed, would be the square root of vx squared plus vy squared, and the angle we are moving off at, theta, would be the arctan of the y component over the x component of the velocity. And so we can just, we can be moving in 2 dimensions here, and we just look at the x velocity and the y velocity separately, and we add them together as vectors. Let's say we had another problem, which we're playing hockey here, and we are moving off in the positive y direction at 8 meters per second. Instead of calling this velocity of the player, I will call it velocity A, just because we have velocity of the puck as well as the player, and both of them start with P. So I'll call this velocity A, and I will call the velocity of the puck velocity B. And let's say we're moving off at 8 meters per second, and we want to hit the puck. We know we're going to hit the puck with a speed of 29 meters per second, and we hit the puck when we are horizontal with the goal here, but because of our forward velocity of 8 meters per second, we're going to have to hit the puck behind us a little bit in order to hit the goal. And so in this case, we want our resultant vector, which would be this v total, to only have a horizontal component. In other words, what we want is we want to have, let's say our resultant vector, I'll call this is a resultant instead of v total. So the resultant is going to be VA plus VB. And like we saw previously with the superposition principle, this means that the x component of the resultant would be the x component of vector A plus the x component of vector B, and the y component of the resultant would be the y component of vector A plus the y component of vector B. And so if we look at the way this was defined, A was going strictly in the y direction, so let's just write out this vector here. So VA is going to be the vector, the x component was 0 and the y component was 8, and the magnitude of this, the units of this are meters per second. And vector B will have both a x and y component. The x component will be the 29 meters per second times the, using reference angles here, and this will be in the fourth quadrant, so the x will be positive. This is 29 cosine of theta. And the y component, because it's in the fourth quadrant, will be negative, so this would be negative 29 sine of theta. And then we can find out, we have two equations and two unknowns. So we have these two equations here with the resultant in x and the resultant in y, and we know that because we wanted it to go perfectly horizontal, we knew that the resultant in the y direction was equal to 0. So let's just plug that in here and say that we have 0 is equal to VAY, which was 8, plus VBY, which was negative 29 sine theta, and then we can solve this for theta. So we have theta is equal to something. And then once we have theta, we can actually find out what our resultant in the x direction is going to be. So the resultant in x will then be equal to VAX, which was 0 plus 29 cosine theta. And so then we can get our magnitude of the resultant in the x direction, which would then we can use this to find the magnitude of the velocity. So we can the method for solving kinematic equations in 2 dimensions, or we haven't even gotten to the kinematic equations yet, but for solving in 2 dimensions is that we look at each dimension individually. So we have here automatically 2 equations with the x direction and the y direction. If we were dealing with 3-dimensional motion, then we would have a third equation in the z direction as well. And so this is the fundamental basis for how we'll apply the kinematic equations in 2 dimensions. So doing this results in the kinematic equations which we previously had. So we had the kinematic equations Vx equals V naught x plus axt, and we also had here delta x is equal to V naught xt plus 1/2 axt squared. We also had Vx squared is equal to V naught x squared plus 2ax delta x, and lastly we had delta x is equal to Vx plus V naught x over 2 times time. So these are the kinematic equations which we've previously introduced. Now I put an x subscript on these because this is strictly for the x direction. We would apply these 4 equations are sort of like just this one equation up here for the resultant in the x direction. That's, we can use any one of them for our equation in the x direction, or any combination of them that we need. But because we're now going to deal with motion in 2 dimensions, we also have the same kinematic equations, Vy equals V naught y plus ayt. We have them all in the y direction as well. So we have here delta y is equal to V naught yt plus 1/2 ay times time squared. Vy squared is equal to V naught y squared plus 2ay delta y. Sorry, that's delta y. And delta y is equal to Vy plus V naught y over 2 times time. So we have just repeating the kinematic equations in the y direction, right? So now instead of having 4 kinematic equations, we have 8 kinematic equations, but they're not really new equations. We just apply them in another direction. And if we had 3 dimensions, then we could have all these duplicated again in the z direction as well. So the fundamentals of kinematics in 2 dimensions are to break the vectors into components and then apply the kinematic equations just for those directions. We can't apply x and y together. Everything in this equation here must be in the y direction. Everything in here must be in the x direction. We can't interchange and put some y stuff in here. I can't say Vx is equal to V naught y plus axt. That doesn't make any sense. So these equations have to be evaluated independently for their respective directions.